It's a pleasure to see you all here. A lot of known faces, a lot of old friends who came over to us today, but also a lot of new faces. And I'm delighted that this topic that we show here today, deep learning, creates a lot of interest. And there's also some people maybe out on the live stream. So obviously this topic that we discussed today creates a lot of attention these days, and to put that a bit into context, let's look back 50 years. So who knows who that is? Some people might know, right? So it's an artificial intelligence character from Stanley Kubrick's masterpiece 2001 Space Odyssey called HAL 9000, and it's an artificial intelligence that controls a spaceship, and at some point it decides to put mission over the life of people and takes control over the ship and doesn't obey the orders of the humans anymore. So I'm sorry, Dave, I'm afraid I can't do that, is one of these phrases from this movie. Obviously, Dave is not amused about that and has to take action. So I think in this milestone, already a lot of today's ethical controversy around AI is already pre-shadowed and made known. So that was 1968. AI was still science fiction, but it was also already in science. So computer scientists and mathematicians developed the ground for AI already back then. So now, 50 years later, the babies of HAL are in your pocket, so here. So if you use them or not, they are there, available, and they may be listening to you. As much as a lot of these other companies are watching and listening to you and collecting your data and creating augmented reality systems based on that. So we have self-driving cars, we have self-operating drones, killing people and other infrastructures. No? So a lot of these things that have been part of science fiction a while ago, also visions from Terminator or Matrix are everyday life, are reality today. And that's obviously why that's a very interesting and hot topic also for us as scientists. So looking at our own area, there have been a few success factors why deep learning is so popular today. So it is enabled by a number of factors, including very prominently the availability of huge amounts of data sets with millions of images, trillions of text samples. So that make this possible. Paired with the availability of immense compute power, the GPU, CPU clusters, and the ability to run some of these computations over weeks to get to results. So all of that made these advances possible, together, of course, with the advancements in the science, in the computational strategies and the algorithms that make use of that infrastructure. So that really brought in our area, visual computing and computer graphics, vision and signal processing, really, it was disruptive. So you can really think of it, the prehistoric times of before deep learning came into place, and the modern times where we use that widely in our research. So it was disruptive for many, and a lot of the old school computer vision and graphics strategies of handcrafting, developing targeted algorithms have been replaced widely by learning systems. So that is a disruption, but also an opportunity. So many researchers around the world took this opportunity and embraced this change and came up with new solutions targeting the old problems with learning-based approaches. And so did we in vSense. So we are a young research team established like 3 years ago, and we fully went into deep learning, looking at all of these topics that we wanted to look at from this new perspective. So although the term deep learning was not even mentioned in my initial proposal that I wrote 4 years ago, now the team is widely working on deep learning solutions. And you see that over the years, So that's a list of publications that we made over the last 2 years. We reached a quite good position with that, I would say. So I would claim that we are one of the leading labs in the country around this type of deep learning for visual computing. We also ramped up our resources, so we have GPUs and all of the compute infrastructure that you would need to do this type of research. But in order to make this also public and available and accessible for ourselves in a way, but also for the local communities of academics and industry, we thought to put together this seminar where we would showcase all of these published papers basically to you, to make you available, aware of these things, and to get into discussion and exchange and stimulate further things around it. So I think it's a unique opportunity to see this breadth of research that is, as I said, covered in a variety of different papers in one place and in one session here this morning. So that's the idea of this seminar. So the format will be, so we will do maybe 1.5 to 2 hours of lectures first, so where all the colleagues that have been working on these projects will give you short pitches. 5 minutes was the target of the individual papers, really hard, giving a high-level pitch, not going into too much details, but stimulating your interest. And then in the second part, we will have the poster session. So you see already all of the posters around you. The researchers will be available for discussions where you can discuss with the individuals around all of these things. And all of this is already available. So all the code, data, and the papers are available on the typical repositories, also accessible through our web pages. And we will also make these slides available, and also the video that is captured will be available afterwards online. So it's an opportunity. Also, we were hoping to get into contact to establish connections to others and to go on with that. Because I believe we have the opportunity here to grow and to establish ourselves as a nation which is active and advanced in these technologies, which will certainly have a lot of benefit. And we were also thinking of maybe how to extend that. So obviously that resonated quite well with a lot of people. So we might do another one next year where it would not be ourselves, but basically everyone would be invited to present published work and to create a forum where deep learning technology would be exchanged in the country. So that might be upcoming for next year, and maybe a sense of community could develop from that, which would make us all stronger in these areas. So with that, I will get into the presentation. So it will be a fast-forward type of exchange. So you will see a lot of the colleagues coming to stage. We won't do questions during this part, but later all of the discussions and questions should happen at the posters. Maybe now, if there are general questions or comments, happy to consider. Well, then I have to start with 3 of these presentations, as some of the postdocs that were members of our team left meanwhile. So they look for permanent positions, obviously, and they were quite successful. So Mathis and Sebastian have good roles in industry, and also Rogerio is professor in Texas meanwhile. So I have to take over these first 3 ones. And the first one looks at the topic of hand-drawn animation, so which is a classical art where so animators have these incredible skills of drawing characters on paper and also putting such shadings and shadows on them, which is a very intuitive process, and highly skilled artists are doing this. And they are not really physically correct, they are non-photorealistic, but they are in a way expressive. And in the digital age, where a lot of the such 2D cartoon art is also done with digital tools, we wanted to create the equivalent for the digital times. So this would be easy if you had a full 3D model, like you see on the left side. Now, if you have a 3D model, you can put a light source and compute physically realistic shadows. But if you have just a 2D sketch or a 2D painting, you don't have a 3D model, and then adding such shadings here becomes a non-trivial problem. So we thought of, can we do something that would automatically allow you to add such shadows, which would not be, as state-of-the-art approaches would do it, take the scenery, inflate it into a full 3D model with highly tedious and interactive tools, and then do a realistic shading. So that was the idea. So the purpose was taken a line drawing as input, generate a normal map, which is basically describing the surface properties, the normal at each point of this object. So we don't need a full 3D model. The normals are enough to compute then these illumination effects. So the question is, can we build a network that can take a line drawing and get you a normal map? And one of the core problems in everything around deep learning is, of course, data. But if you are in such a problem where it's not natural data, natural video, images, audio, but something which can be generated by computers, then this problem becomes easier. So you can, for instance, take a lot of 3D models that you can easily get from databases like this one. You can render line drawings out of this in a lot of possible poses. So you just do that from the model, and you can render the ground truth normal maps from that. So the whole data set can be generated from a couple of available models. So that's what Matisse did. He took a couple of hundred models, and each of them was rendered in dozens of different poses, and he generated the input and the output, and basically that's what you need to train a model. He then designed a quite standard U-shaped encoder-decoder structure, so there's nothing too fancy around the network here, but of course the tuning and the training of the network required some research and knowledge. But he came up with a system that could then basically do what you see here. So it takes pure 2D line drawings as input, creates automatically the normal maps, and then you can position your light source wherever you want and create such shadings. So it's a tool for artists that we also have integrated into a drawing tool, where such shading effects can be done, right? There always has to be a teapot in these computer graphics applications. Of course, we can also relight the teapots. And this also extends quite easily to animation sequences. So here is one of our own drawings with a candle, and you see that. Yeah, so here you see the same thing for sequences. So left the input, the estimated sequence of normal maps, and the final rendering that was created. Now, and certainly this is a principle that can also be extended to a number of other things. So estimating full 3D models is obviously something that you can do here, estimating of full depth maps. And that's something that we already submitted as an extension of the current work. So just taking a sketch as input and creating a normal map and a full 3D model is something that is already available. So this was the work of Matisse, who I know is on the live stream. So thanks, Matisse, for that. And in his next work, Matisse also got together with another colleague who left, and he's now with TU Berlin as a senior researcher about interactive depth map creation. And Sebastian is an expert in depth map creation because he had already a startup in this area. And the background in this is, again, professional production, and in particular 2D to 3D conversion of movies. No? So if you look today in the cinema at any of the movies in 3D, none of this is actually captured with a stereo camera set. 99% of the images you see are converted from the 2D version into 3D. And the typical workflow here is that you take the 2D images and you have people who are drawing a per pixel depth map. So really, it's a fully artist-driven process. And if you have an image and a depth map, you can generate by depth image-based rendering a second image to that and convert monoscopic video to stereoscopic video. So that's, of course, a highly expensive and cumbersome process, and any automation in that will be very welcome. So what Sebastian did with his company was developing tools for 2D to 3D conversion in studio environments, where you would, for instance, not for every pixel give a depth value, but maybe just do rough scribbles, and those scribbles would be propagated by a nonlinear edge-aware diffusion process into the full depth map. So here you see this interactive tool by the company ImCube, where a skilled artist is interacting here, so drawing scribbles onto these images which correspond to certain depth values. And here you see how the depth structure of the scenery is evolving, and here you see how the depth map is getting better and better with each of the inputs that the artist is doing. And so the artist is continuing until the depth map that is generated is of sufficient quality, and the stereoscopic view that you see on the right down there that you can view with some goggles is of satisfying quality. And you see that although this is better than painting every single pixel, it is still a tedious and cumbersome process, but something that is used in this way today in production. So now if you want to do this for every frame of the video, it's still a lot of work. So people have been already thinking about, well, what if I can do it just on a number of keyframes, then propagate the information to the in-between views. And in the old days, that has been done by optical flow. So you have the video sequence, you can estimate the optical flow in between the images. If you have the depth map, you can also propagate the depth to the intermediate. But optical flow is old school, and today we can do this with deep learning. So the idea was to build a framework architecture like that. So this is the input, which is the image sequence, and this is the output, which is the depth sequence. And now for a number of keyframes, like every fifth frame or so, we have this artist-driven process that you just saw, that we take each of these red frames and generate a depth map for each of those frames, so for the red ones. But then the color frame and this generated depth map go into a network, which is again a quite straightforward U-shaped network, which has basically the color frame as input and the depth map as a target output. So it learns how to generate a depth map from an image, and then it can basically propagate this information and generate all these intermediate depth maps automatically. And in this case, we train the network on the actual images and depth maps that were created. So we again generated a data set where we had full depth maps for the whole sequences. So we had all of these depth maps for the training. No, that's wrong. So we only use the red ones as input and generate a network which is overfitted for this particular sequence. So it's a disposable network. It works for this particular sequence, but in this case, overfitting is a good thing because we just want to generate those views for that particular sequence. And here you see the results. So this is the color sequence with the scribbles, and this is the ground truth depth map that was generated for these keyframes. These are the depth maps generated from the scribbles. This is this diffusion process, which is a little bit different than the ground truth. And this is the ground truth intermediate depth maps. That's generated by optical flow, and that's generated by the deep learning. And you see that optical flow is doing a good job, but the deep learning is better in that case. No? And that was also quite a nice success, and we submitted that to a conference which is partially addressing technical papers and partially also artists, and we got the Best Paper Award there, which is the Lumiere Award, and the Lumiere Award is also given to artists at that conference, so David Cameron also has a Lumiere Award as well as we have. So here you see Sebastian receiving this award. So the next and final thing I want to present is again addressing something from professional film production. It's about human motion capture data. So these are data produced in professional production where an actor dresses up with a suit with markers on it, and there is a highly complex motion capture system installed that tracks the motion of a person. And this motion is then converted into a time sequence of 3D coordinates that is corresponding to these joints. So that's the motion captured sequence, a time sequence of such coordinates. And these time sequences are then used to animate something like Gollum or like a virtual character that is then being inserted into the movie. And one thing that in professional production typically happens is that they create all of these data for a certain movie, but they are later not able to reuse them or to have data being used for different productions. So working in an EU project with partners from the London post-production industry, we had the idea of can we automatically classify such motion capture sequences? No? So can you, just looking at this time sequence of the data, say, well, this is a jump, this is a run or a walk, no? And then that would be make these databases of available motion capture data available to new productions. So retargeting, reuse of objects is here the background. So the first problem, as always, is getting the right data. And it's basically impossible to get any real data that you have from film industry, but we were lucky that Carnegie Mellon University had a data set of motion capture sequences, and but that were just the raw sequences, so we first had to make sense out of them, to label them, to create these data. So we cut the sequences into meaningful pieces, and we assigned them a certain label, like climbing, dancing, fighting, and we created a data set with 9 different categories and had a certain amount of data for each of these categories. So this is time sequence data, and the typical approach for something like that might be an LSTM, a recurrent neural network. We again used a quite standard off-the-shelf LSTM structure then to train networks on these input data and to try to predict these labels of what the motion capture in the sequence is. So we first tried that with all the 9 different labels we had. And you see that so these are different parameters that we used in these experiments. And you see that we were quite poor in the results. So we only had like something about 50% recognition rate. And also, if you look at the confusion matrix, so here are the different actions that were part of this data set and how they were confused with other actions, you see that the performance is pretty poor, pretty random. So what's the problem here? So obviously, we didn't have really a lot of data, so underfitting might be a problem. So then the idea was, well, we also looking at the data set, there were some of these categories where we had more data. So we thought like, so let's make a test, let's try using just those categories where we have a lot of data. So we reduced the number of labels and also used just those data where we have most available things. And you see, well, that improves. So we got over 70%, and also the confusion among those is much better. But here we are solving a much simpler problem, obviously. So the next thing was analyzing these data. There were actually some of these categories that were quite distinct, that already in the first place could be recognized pretty well. So then in the final experiment, we decided to use only those. And luckily, we were able really to show that we were able to, over 95%, we were able to recognize these different actions, and the confusion matrix was also quite nice in this case. So this is a proof of concept, obviously, only that this type of motion capture classification based on deep learning is possible, but also highlighting that, well, you really need a sufficient data set to do any, and that's something that's true for all of what we're doing to have meaningful results in deep learning. And that was also published by Rogerio at VisiGraph last year. So certainly we would continue. So this work opens opportunity for more work if you have more data. So that's enough from me, and then I call Sebastian to take over for the next part.
Good morning, everyone. I'm here to tell you a bit about natural image matching. So the first question you may have is, what is even natural image matching? And it's a problem where you have a natural image, so any kind of image, and you want to extract the foreground object from the background. And you want also to consider the opacity of the object. So if there's maybe translucent cloth or anything like that, you want to take that into account. So mathematically, this is formulated quite easily. It's just a linear combination of the foreground with the background. However, it's a quite ill-posed problem because you have three known values, the RGB values of your final image that you see, but you have 7 unknown values, the RGB value of the foreground, of the background, and this blending factor, the alpha. So to help with that, often people use trimaps to help guide the algorithm and initialize it. So as you can see here, it's a kind of rough segmentation where everything that's definitely the foreground you color in white, everything that is definitely the background you color in black, and everything where you're not so sure about is the unknown region in gray. So the more effort you spend on this, the better your final outcome is probably going to be. I mean, if you just color everything gray, it's probably not going to work too well. So our contribution with this project was the first generative adversarial network for image matching. So we have a generator, which is a convolutional neural network that takes the image and the trimap as input and estimates a high quality alpha in a quite fast manner. And we also have a discriminator that is supposed to differentiate between images that have been composited with the ground truth alpha and with the predicted alpha. So the discriminator actually learns how to tell how good a composition is. So our network architecture is, well, not too special. The generator, as I said, takes as input the RGB image and the trimap, so 4 channels. It's an encoder-decoder structure, and we also have some skip connection to add more local information. And the discriminator architecture, we take the patch-GAN from another paper, Pix2Pix, and this one has been designed specifically to capture high-frequency structures. So if you have something like hair, for example, then this discriminator has been designed to more easily be able to tell in these regions which one is fake and which one is real. So how does the training work? So first of all, we take a ground truth foreground object. Where's the mouse? You can see it here. And we take the ground truth alpha and a random background, and we composite a whole new image here. And then we get a random trimap by dilating from the ground truth alpha, and we feed that to the generator, which then predicts the alpha, which is hopefully going to be as good as the ground truth. Then with this predicted alpha and the same foreground and the same background, we composite a new image. Now, in the ideal case, both of these images would be more or less exactly the same, right? So we feed both of these images to the discriminator, which is trained to decide which one is real, which one is fake. So we want good composition, right? We want compositions that are as good as compositions that were done with the ground truth alpha. And the discriminator is trained to do that. So some of the results here to the right, this is ours. As you can maybe see here, I don't know if it's easily visible on the projector, but we are very easily able to capture these fine hair-like structures, and we don't have any weird artifacts like some of the other approaches have here. So our approach works especially in these high-frequency structures. It's the same here. And if you want more results, the poster is back there, so you're of course then welcome to come. So in conclusion, we have a novel architecture that predicts alphas that lead to visually appealing results, and the adversarial loss especially leads to the ability to capture high-frequency structures. The work is not quite done, so we are also working on, for example, estimating the foreground color, which is also kind of necessary if you want to have the real perfect new compositions, and even to add maybe some temporal coherency. So that's for this project. I'm also going to talk to you a bit about lens distortion. So every camera lens introduces some kind of lens distortion. So you can see it here in the example. The street is, in real life, it's supposed to be straight, right? But the lens adds this kind of distortion. And often this is a quite artistic choice of the photographer. So for landscape shots, you would generally use wide-angle lenses, while for portrait, you really wouldn't want to do that. But it can be also important to remove the lens distortion for various reasons. For example, for CGI, if you wanted to mask out the street here in this example, for the street, wait, I forgot how I started the sentence. So if you wanted to mask out the street, it would be easier to remove the lens distortion and have a straight edge here and just mask out the street and then reapply the lens distortion. So that would be easier as if doing it straight on this image. So just a bit of background. Typically the lenses have radial symmetric distortions. So there's typically two kinds of distortions, barrel distortions and pinhole distortions. And yeah, if you have the parameters of the distortion, it's quite easy to reverse them. But getting these parameters from an image can be a problem that we are trying to solve. So our contribution is a neural network that can estimate these distortion parameters directly from an image. And the parameters, they correspond to the Fitzgibbon's division model, which is quite popular. And there has been previous work done in this. And some of them, they try to directly rectify the image. So basically, they have the distorted image as an input and have a rectified image as an output. However, if you have high-resolution images, they won't fit into a network. So what they would have to do is downscale the image, rectify it, and then upscale it again. But that just, it adds noise, and it's not that great. So we deliberately made the choice to only predict the parameters. So then we can, downscale the image, predict the parameters, and then use these parameters on the high-resolution image to rectify it. So the network is relatively standard. We use exception as a convolutional backbone to extract dense features. And then this final feature map is multiplied with a squared radial distance from the center. So in the distorted image, the distortion is most heavily apparent at the edges of the image, right? So with this radial distance map, the middle of the feature maps will have only zeros, and the outsides will have ones. So basically, the outside features are weighted more heavily, because that's where the distortion is more apparent. Then we use some convolutions to reduce the number of feature maps before flattening this into a vector. And then we use two branches of fully connected layers to predict both the distortion center and the distortion denominators. So experimentally, we created a set of Dublin city scenes where we carefully rectified these images manually. And then we deliberately chose some scenes where there's a lot of straight lines and some where there's none. So if you wanted to manually rectify an image, it's doable if you have a lot of straight lines, because basically you know a line is straight, but in the distorted image it's curved, so you kind of want to straighten out that curved line. But it's a cumbersome process, and if there is no straight lines, then well, you're kind of out of luck. And then finally, we randomly distorted these manually rectified images for a variety of lens distortion effects. And you can see some results here. So on the left are the distorted images. So you can see here these barriers here and here. They are not straight, even though they're supposed to be. And this is our prediction, and this is the ground truth. So it's quite close. Maybe not perfect, but it definitely does work. So in conclusion, we built a convolutional neural network that can predict multiple lens distortion parameters for the Fitzgibbon division model. And it is a fully automatic model that directly estimates the parameters, which we can then use to rectify even high quality or high resolution images. And we can even use this method maybe as a part of an automatic pipeline for methods that actually need or assume the idealized pinhole camera model, so meaning no distortion, for example, 3D reconstruction. So yeah, if you're interested to hear more on this, the poster for this is also in this corner, so I'll be free to answer any questions. Yeah, thanks. And the next one is Tejo. And also, I'm supposed to mention that the lens distortion paper was together with the Foundry. I see Dan over there, which is, they do software for professional film compositing. So if you've ever seen a Hollywood movie, they probably use their software because it's great.
Hello everyone, good morning. I'm going to talk about using deep learning to do ego gesture recognition. So yeah, this is just the structure what we would go through. But so before we actually try to see what ego gesture recognition is, we need to know what ego gesture, or egocentric vision means, right? So in essence, it's egocentric vision is analyzing images, okay, from any that are coming from variable cameras. So by extension, egocentric gestures or gestures are seen by, through the perspective of a variable camera that's usually on your head. Has anyone here used a HoloLens or Magic Leap before? Okay. If you have used it, it's generally, especially HoloLens, they do like natural gestures like pinch and moving the objects around, right? And you know how painful it is because the set of gestures is very limited, okay? So what we try to do here is we actually try to solve that problem of just recognizing ego gestures. So what are the problems that we get for recognizing ego gestures? So we had to deal with these many issues. So there is varying skin tones, and then there's also varying backgrounds because you just don't want to use your device at one place. And then there is ego motion, which is introduced by movement of your head when you're wearing the device, and then the gestures can be different kinds, static, dynamic gestures. And on top of that, there's also motion blur that comes with the cheap quality cameras that are there on the devices. So deep learning is a very viable solution to deal with all these problems in one go very robustly. Okay, so then, in that sense, now that we choose deep learning as a solution for this, but in itself it brings its own problems, as in it needs a lot of data, right? Anyone who has worked with deep learning knows here that it needs a lot of data. And why do we need a lot of data? Because there are like millions and millions of parameters to estimate for your network. So if you don't have a lot of data, you'd end up overfitting the data. So we don't want that. We need something to generalize your data sets, training data better, or testing data better. So to overcome that, what we did was we introduced this concept of green screen data set, where you can perform your gestures in front of a green screen. that would automatically create masks for your hands, right? So in that sense, you don't need to manually go and annotate the data set, taking the pain away of manual annotations for your data. So we published this data set. It's available on our servers. I'll show you a link later which is at the poster. So this is one of our first works that we did, and we published the data set along with the results on the data set to ISMAR. And also then we'll quickly look at another data set called the Ego Gesture data set, which is one of the largest publicly available data sets. Someone painstakingly went through the process of 50 subjects going around performing the 83 different gestures in different environments. This is like a benchmark data set for egocentric gesture recognition. So now that we have looked at 2 data sets, we'll just briefly look at the network architecture. I don't want to go into the too much details of it, but this is the general idea. You have an encoder which would take an RGB image of your ego hands, and it would reduce the representation to something smaller, and that's the same smaller representation is sent to a decoder to actually reconstruct your ego hand that's in front of it, and at the same time it's also sent to an LSTM as a sequence to actually understand what the gesture is in your sequence of images. Okay. Some pretty results here. If you see those are the RGB images on the left hand top corner, and the one in between is the noisy data that we get from the ground truth, and the one after that is the rectified, the masks, the ego hand masks that we were able to get with our network. And these are just some activation maps showing that our network is actually finding the right parts of the image wherever there is an ego hand. You can see that it's actually the heat map is red. That means the network is correctly identifying the ego hands. So I'll run through quick results on this one. So one of the things is, if you see the accuracy, there are 2 kinds of accuracies that we are doing here. One is frame level and sequence level. Frame level is if you take individual frames, right, of RGB images, and we try to see what gesture is in it. We get about 58.3% for 10 gestures on our data set, which is not great. But if we use the sequence level accuracy through LSTMs, we get 71.42. And if you see the confusion matrix, the good things with confusion matrix are they're very easy to analyze. If the diagonals are much brighter than the rest of the matrix, that means it's good. It's a very simple device to analyze your results. So if you see here, the diagonals are not like that great because you just have 71.42% accuracy, but it's still not bad. But the good part is the results on the bigger data set, which is much better. So if you see, the state of art is 92.2%, but we actually bet it by quite a large margin with 96.9%, and some more evaluation results out there. And yeah, that's about it. I know I've actually talked very fast and I haven't given any details. I talked more like a current politician more than a scientist. So if any of you are interested in more details, I'm by the Campanile. So stop by, and I'm more than happy to discuss LSTMs or egocentric gesture recognition. So.
Okay. Morning, everyone. I'll be presenting aesthetic analysis of photographic images. So aesthetic analysis of photographic images refer to analyzing the properties of a photographic image, unlike natural images that we are familiar with, to decide whether what are the properties that make them look aesthetically pleasing or dull. For example, we will be discussing 2 different aspects of aesthetic analysis. One would be the analysis itself, which is finding the factors which make it look aesthetically pleasing as in the left one. And the other one would be giving feedback, which is an image captioning work, which basically given a photograph, the task is to generate photographic feedback or critical feedback in a textual form. So coming to topic 1, which is analysis, this is what we did. So given a picture of Yosemite National Park, I suppose, the task was to predict the aspects which make it look aesthetically pleasing. So as you can see, this is a grayscale image, so and it's also a high dynamic range picture. So HDR comes at the top, followed by duotones, which is the grayscale itself, then long exposure, rule of thirds, etc., etc. So what we did was incrementing certain aspects of the general convolutional filters. So this here you can see the standard convolutional filters. How it works is given an input. We have a set of filters which operate on the input image and gives us feature maps. So in principle, by the convolutional filters are made translation invariant. That is, they move all around the image to give a filters and they share weights among each other. What it means is they're made translation invariant. So if given these two images, the image of a face and the image of a face randomized, both would mean the same thing to a standard convolutional network, because the features are local and the features maps are created by translating each filter and by sharing weights across the image. So essentially the convolutional neural network is translation invariant and appearance cognizant. But in photographic images, this property of translation invariance is sometimes not desirable. For example, in the rule of thirds, sometimes the position of the object is crucial. For example, the position of this cow in this particular juncture makes it conform to the rule of thirds, which is important for composition. Or the line along the horizon is also important for composition. As you can see, this aligns with this particular lines, these grids. So position of the main subject is crucial for framing. So what we did, we found that saliency of an image does in fact give us an information about the position of the main subject of an image, which in turn helps us to understand rule of thirds better. So along with the normal RGB features, we proposed a double column architecture of a CNN. In one column we pass the saliency and in the other column we pass the RGB features, fuse them at this level and then finally give the prediction. The idea was that by fusing saliency and RGB together, we might have a better understanding of the position or the rule of thirds properties or geometric aspects of the image. So essentially we make the features location cognizant and appearance invariant from the translation invariant and appearance cognizant aspect. And for more quantitative results, the poster is on that corner. I'll be happy to show you the more quantitative results for this work. So this is the next topic, which is feedback, and the task was to, given an image, describe the image in a textual format. For example, for this image, a textual feedback would be nice landscape, short, but the tones are a bit heavy. So this is how a traditional image captioning problem works. Given an input image, a CNN extracts the visual features, which are then fed to an LSTM or a long and short term memory or a recurrent neural net, which gives the textual feedback for the image. In general, for training this kind of a network, what we need is a large data set with an image caption correspondence. For example, we have MS COCO captions, which have about 100,000 images with 5 captions per image and is clean and was annotated carefully for this particular purpose. But when we want to do something with aesthetic image captioning, we don't have a well annotated or clean data set. What we have is a lot of unlabeled or noisy data from the web. For example, as we see in Flickr, in this case we use AVA, which was collected from DP Challenge, which is very similar to Flickr. As you can see from the comments, these are very noisy and not curated for this particular task. For example, 1 and 2 would be really noisy. The next 2 would be decent. The third one would be too informative or too difficult to learn. So unlike MS COCO, it would be very challenging to train a CNN LSTM framework using such noisy data set. So we made 3 contributions in this particular work. The first step was denoising the data set. we proposed a scoring strategy which was based on the observation that certain engrams, as you can see, post-processing or trees or background, softness, such are the words which are more informative than others. Based on this intuition, we proposed a scoring strategy which scored each caption, and we filtered some of the noisy comments based on this scoring strategy. Once the dataset was available, what we proposed next was a weekly supervised CNN training strategy. Now this was done to aid in practical or commercial scenarios where you don't have datasets as big as ImageNet or CNN training datasets available. We proposed this strategy which can be used to discover photographic clusters using the comments and then use them to train the CNN and give us visual feature extractor. The final phase or the final framework of this pipeline was use this visual feature extractor, take an image, get the visual features and feed it to an LSTM in the traditional way and get the predicted text, which is the caption. So this was the overall contribution to generate captions, and this poster, the second poster is also along that corner, so you're welcome to ask more questions and see more results. Thank you.
Hi, so my name's AlphaGAN and I'll be presenting SalNet 360 saliency estimation for 360-degree viewer images. And this work was done by my colleagues Rafa, Sebastian, Tejo, and Alyosha. So first of all, I'll just give some background. So on saliency, so salient regions of a scene are the pertinent regions that stand out from the rest. These are typically where people look when they're viewing a scene. And the ground truth data is captured by tracking people's eyes and where they're looking when viewing a scene. So a scene can be images or videos, or in our case, omnidirectional images. So what are these? An image, these are images obtained from an omnidirectional 360-degree camera, where the viewer, field of view is the full circle in the horizontal plane, or you can think of it as capturing the sphere. So these can be stored as a 2D image by using projections, as you can see here on the image on the right. So why should we be interested in these? Well, the viewer market is expected to continue to grow, and one of the ways we can use these devices is to visualize 360-degree images or video. And this technology is becoming more and more accessible as the devices to capture the 360-degree images, as well as the devices to display them, are becoming cheaper. So what unique problems do these pose for saliency prediction? So as you can see here in this image, it gets very distorted on the poles, so on the top and the bottom. That's because if you imagine you're standing within a sphere, looking around, you can see everything, whereas when you project that onto a 2D plane, the poles become distorted. So along the bottom here, you can see that there's kind of a green and white smudge, and we're not really sure what that is. But if you just take a selection of the bottom of the sphere and you project that selection onto a 2D image, you can see the object in question is a cake up here on the top right. So when you're trying to predict saliency, you might be taking into account the shape of objects, and if the object here is a big smudge, you won't be able to detect what it is, in this case a cake. Another problem that these images pose is that when you're typically predicting saliency for 2D images, you get this, people typically look at the center more than they look at the periphery. This is called center bias, whereas with an omnidirectional image, you don't really have a center in the same way. So yeah, this is another problem that's unique to omnidirectional images. So our proposed solution, or our solution, to this was SalNet 360. So we take as input an omnidirectional image. We split it up into these patches. So you have 6 patches. You can think of that as like, instead of within a sphere, you're within a cube. So it's the 6 sides of the cube. These are then fed through a convolutional neural network. and then the output is the saliency heat maps of these patches. These are then combined together by projecting the pixels of the patches onto the corresponding pixels of the omnidirectional image, interpolating them, and then using a Gaussian filter to smooth and fill in the holes. And then you're finally left with a saliency heat map of the omnidirectional image. So a little bit about the architecture. So you start off with your input is the patches of the omnidirectional image. These are fed through a base CNN. So it takes these 2D images as input. It trains them using a data set of normal image or regular images. And then the output of this is a traditional 2D map of 2D images. So then these are then combined with the spherical coordinates that link the pixels on the patches to the pixels on the sphere, which in turn is mapped to, or is a mapping to the corresponding pixels on the omnidirectional image. So we pass the saliency map and the spherical coordinates through another convolutional neural network, and these are trained on undistorted omnidirectional image patches, which are obtained by randomly obtaining patches from the omnidirectional images, in the training set. So, and then finally, the output of this convolutional neural network is the saliency map of the patches, which are then combined to obtain a saliency map of the omnidirectional image. So here are the results of the SalNet 360. So I'll just give you a second. The ground truth is up there on the right. I'm not sure why it got changed, but anyway, it's up on the top right-hand corner. So you can compare this to the base CNN, the base CNN plus the patches, and the base CNN and patches and spherical coordinates. So if you take a quick look, you can see that the base CNN and the base CNN plus patches have incorrectly assigned salient regions to areas that are not salient in the ground truth, whereas the base CNN plus the patches plus the spherical coordinates are then, more accurately is similar to the ground truth. And this, so here you can see qualitatively this approach is the best, and that's also backed up by the numerical results. So finally, I'll just recap. So here, SalNet 360 was used to predict saliency of omnidirectional images, and these posed problems such as there was a lot of distortion in the 2D representation of the omnidirectional images, and we tried to solve that. We also tried to solve the problem of typical images have center bias, whereas omnidirectional images, the center is a bit different, or where people look is a bit different. And the solution was SalNet 360. Thanks very much.
Good morning, everyone. And my name is Xu. It's my pleasure to be here today. And I graduated from Trinity last year. And the topic today I'm going to present is a data augmentation technique based on style transfer. All the researcher just now has mentioned that they required lots of data, but in the real world, we cannot get enough data at most of the time. So data augmentation has been used a lot, and it has been found an effective way to improve the performance of the model. The traditional data augmentation techniques include flipping, rotation, and cropping, but it can only add limited data. Like if you take a picture in a sunny day, the model cannot learn it if it's in the rainy day. So this is where the style transfer can work. This is the general architecture of the style transfer model. I will not go deep into it, but there are two networks in this model. The first one is a transformation network. It can create a new image, and the second one is a loss network, where it can compute a style loss with a style target and a content loss with a content target. And the linear combination of these two laws will help the transformation network to learn the style. After this transformation network get well trained, the style information can be encoded in this network. This is a stylized image we created in this work. As we can see, in the first row is a original content image, and the following rows are the stylized image. We can clearly see the content, semantic content are kept, where each of them have a different style, even different color and different background. In our work, we choose 8 different styles and trained different transformation network. In this stage, we dropped the loss network and use this transformation network to enlarge our data sets. Each content image get 8 different stylized image. We will use this image with the original image to feed a classification network, which is 16 and which is 19. Here is our results. It's very impressive because 7 out of 8 styles works better than the traditional technology, flip and flip rotation. And and we also combined different styles together and even changed the weights between the content and the style. But we didn't bigger change by the combination. The same experiment has been performed on another network, which is 19, and we can also observe the considerable improvement in terms of the classification performance. So this means that our approach can generalize well across different architecture. So here is the conclusion. Our experiments has shown that style transfer can work well in image classification task, and we have observed 2% boost in terms of classification performance. But our only image classification task has been tested in our experiments. So as for future work, we can use this method on other image tasks like image recognition. And better style transfer algorithm can be used like AlphaGAN because this method is independent of architecture and algorithm. So I got a poster there. I will be there. So you are welcome if you have any questions. Thank you.
Maybe just shortly, so just to make it clear, so that was a work done in a master's thesis last year, and Ju did his master's with us and is now with Egocentric here.
So hello everyone, I'm Akanksha. I'm going to present a couple of works, so please bear with me. I'll start with the very classical problem of super resolution for omnidirectional images and done using adversarial learning. So as you have already heard about the omnidirectional images, it's a very important imaging format for immersive technologies. And for VR system in specific, this very high resolution content is basically very important for the very high immersivity of the user. However, with our current technology that we have to capture these things, it's not up to the mark. Therefore, super resolution becomes very important. So in this particular work, we are focusing on the super resolution problem for an equirectangular projection because this is the most default format of the omnidirectional content. And super resolution literature has basically improved significantly from the interpolation methods, which were very classic, to the learning-based models like CNN and GANs. So we got inspired from the same idea, and we proposed a deep learning-based super resolution model for ODI. And our basic motivation to do this was to handle the artifacts which are basically obtained in the spherical observational space in general. So we propose our model based on an SR-GAN framework, where we adopt the generator from an SR-GAN, which is a very fundamental generator network for the super resolution problem. And we try to optimize it with a patch-GAN discriminator. We tried to train it with the patch-GAN discriminator, which is a very fast learning discriminator, very different from the SR-GAN framework. And to handle the specific spherical projection artifacts, we propose an additional loss function, which is a weighted structural symmetrical loss, which is a smarter loss and helps to train the network better. So our 360 SSIM loss is basically a weighted loss, which try to stretch the ratio of an area from the projected planar surface to the spherical surface and helps to get a weighted values for the pixels, which are to be trained in accordance with the spherical content. So we trained this model for 4,000 ODI images which we had in abundance. So we observed that we were able to curve the artifacts very much in the spherical projection space, as you can see here. I think the better clarity images will be obtained will be observed in our poster session over here. And to know more about this, you can just go to the poster session. And just to mention, this is the first work in the ODI super resolution area. And our goal is basically to improve and apply this proposed method in the ODI streaming application scenario. So this work will be presented in poster session by Simone, one of our colleagues, so it's just there. So the second work is towards generating ambisonics using audiovisual cue for virtual reality applications. So immersivity in VR is very important, as we all know. It's one of the most important thing that is kind of being discovered in the virtual reality and augmented reality domain. The basic problem with most of the current methods is that they basically use a single stimuli at once. So either they are working with audio or they are working with visual part. But based on the human perception, it's a very complex procedure of how we perceive the different stimuli at the same time. So in this work, we focused on audio-visual analysis for the first time in the immersive VR setting. And we aim to generate the idea of ambisonics using the visual cue and a mono audio signal. So for total immersiveness, ambisonics play a very important role. Ambisonics in general means a full sphere surround sound format, so you get an idea of a spatial sound. And for a full immersive VR setting, this ambisonics can play a very important role because it can help you to localize in an environment and give you the true sense of being there in the VR setting. However, what we have in the present scenario is a very basic framework. We have a simple audio setting, a mono audio recorder, or we have a 6 degree of freedom. So what we want to solve this problem with ambisonic is that we want to generate an ambisonic environment using the mono signal. So to this problem, we propose a two-step solution. Firstly, there was absolutely no data in this domain, so we created a manually labeled data set of 265 audiovisual clips, which are of 10 seconds, very well annotated with respect to the sound direction and the location. It consists of different types of complex and simple scenarios with multiple speakers and single audio speakers and overlapping sounds. And then we proposed an ambisonic generation pipeline, which is a 4-stage pipeline, including the representation, embedding, prediction, and encoding framework. And additionally, we also proposed a metric, because we are one of the first in this area, so we also had to take the responsibility to also measure this problem very well. So we proposed 2 different metrics of 360 sound source distance and overlap error. We also proposed a benchmarking study because we did not have any existing framework, so we tried to adopt some models for our prediction module, which were done for a 2D image, 2D video settings, and we tried to put it in our framework and try to analyze how it performs. So I'd like to mention that this paper has given a special credit for basically emerging a new research direction by Multimedia Technical Committee of Computer Society, IEEE Computer Society. To know more about this and to know more about its results, you can go to the poster session here. I think all my posters are surrounded here, so feel free to come there. The next work is deep tone mapping operator for high dynamic range imaging. Now we move a little bit from the 360 towards HDR imaging. So what is HDR? It's a very special type of image which gives you the idea of a real world view. So it has the ability to capture very wide range of luminance and radiance. So when you see the image, it looks as much as natural as you see through your own eyes. So it preserves detail from the very bright and dark regions. It has the high contrast, color gamut, and luminance values, and it is stored using a 32-bit HDR or EXR format. It has a wide areas of applications using automotive, surveillance, and medical imaging, etc. The one very classic problem in HDR is tone mapping, which is making this scene or making this content visible on a normal 8-bit display screens. So several studies have been carried out in this domain where local and global operators were designed. However, they had their own problems. First thing is they work only for a handful of scenes. So some can work only for a daytime scene, or some can work for a nighttime scene, or some are more customized for one type of scene or the other. And it also requires an extensive parameter tuning for every scene that you want to visualize. And then it's very slow and tedious. This brings us to a very normal goal that we want something more automatic, something which can give us a very high resolution output, which is artifact free and which is a very high resolution quality. So our idea was to start with designing an automated approach, but at the same time we did not have much of a data, or we did not have much of a subjective ground truth for this. So our motivation lied in the idea that why can't we learn from this manifold of available tone mapping operators, and we design something more superior functionality which can counter all these problems together. So we did some primary explorations. We gathered a data set of some images. We generated their ground truth using an automated approach. Then we explored several existing architectures and how to perform for this image-to-image translation, because it was a little bit more explored area. But when nothing worked, we tried to propose a new tone mapping operator, which is based on a CGAN approach. And it's a bi-scale, two-scale generator discriminator architecture, which was working on 2 different levels so that it can cater the artifacts in HDR tone mapping in a very specific way. We explored the different functions of different loss functions and their importance in learning this pipeline, impacts of different normalization techniques, the impacts of different scales of the 2 generators and the discriminators. And we also show you some results here that we can see that our the second column is basically what is proposed by the deep tone mapping operator, and the other 2 are the 2 best performing state-of-the-art tone mapping operators, and we can see that they are much more realistic or subjectively high quality. Similarly here, especially in the nighttime scene, you can see that we just completely curb all the noises which can be generated in this method. For more quantitative results, we also found that we were very, very close to all the best performing, and we were even outperforming in overall performance. We also did some subjective analysis for this, and we observed that our model was doing very well. To know more about this, the poster is over there. You can come up with any questions you have. So the last is the color net toward estimating colorfulness in natural images. So we all know that color is very crucial because we all live in a colorful world, and it has been studied in the literature to estimate how the color and its properties in very different pipelines, like color grading, corrections, for tone mapping, and it is also very important for different types of applications and to different areas of research. So we have some study done in this direction. However, there has been no metric, or there has been no wide-scale study being done using deep learning approach. So this was also the first attempt to study color from a deep learning perspective. So here also we proposed a 2-step solution. We collected a data set of 180 images with subjective colorfulness scores, and then we proposed a deep learning based framework which was able to predict the colorfulness scores out of every image. So to gather the data set, we first found 2 different data studies which were done subjectively on 84 and 96 images using EPFL and UCL data set in a different settings as well. But we proposed a method to, we also aligned proposed a method to align the 2 data set with a low cost common set approach, where the 2 data sets were aligned using a subjective study. And then we proposed a network, which is basically a two-stage network using a feature network and a rating network. First network was basically trying to capture the color features specifically needed for this task, and then a rating network which was mapping the feature information to the colorfulness score. So for the feature part, we basically build on the three very existing architectures, VGG, ResNet, and MobileNet. And then we use a simple loss function, which was basically an absolute difference between the predicted and the absolute value. We observed that our deep learning based method was giving us very high performance compared to the other state-of-the-art method, especially with the VGG framework. Qualitatively also, there are some results. And to know more about this, we have a quality expert who is going to be presenting this poster there. And so this is also an initial work towards the color perception natural images. We are trying to delve deeper into this problem, and we are trying to see what factors really helps us to decide how colorful or how beautiful, the image is. So thank you very much.
Yeah, just to mention, well, you saw this breadth of work that Akanksha was involved here, and it will be a big loss and pity for us in vSense that she will join a Harvard institution quite soon, next month.
Hello everyone, I'm Susanna, and I'm going to present our work about Dublin City, which consists of an annotated point cloud and its applications. Well, first of all, I want to start explaining the motivation behind this work. We knew that there was available a really huge LiDAR point cloud of the city of Dublin, and it was really dense and accurate, and it looks like something like this. And we want to take advantage of this, and we thought that having something like this with semantic information where we can distinguish the buildings, the roads, the trees will be very valuable. So building upon this idea, we decided to create a ground truth that can be used to develop scene understanding algorithms for point clouds and at city scale. The initial data set was captured in 2015, and it has three different elements, which were the LiDAR point cloud that covers the whole city, and you can see them on the left, and then two different kind of images that were captured in the same flight with a helicopter, and there was captured with a top-down view, one of them, and the other with a tilted camera of approximately 45 degrees. And we decided to annotate the area of the LiDAR point cloud, which is inside the red boxes there. And we make it publicly available. And the main features that make this dataset unique is the density of the point cloud, and also the details in the annotations. We did it in a hierarchical way, going from the coarsest elements, a building, ground, vegetation, to details such as windows. We use this data set to see how it can be used for example, object classification. And to see the performance of this dataset, we used three different state-of-the-art CNN-based models. That was PointNet, PointNet++, and SONet. And we used a dataset of 4,000 elements with 5 different classes. And we found out that SONet gave us the best results. However, we also can see that there's still a lot of room for improvement, and this is because the dataset is challenging in terms of similarity of some of the classes, for example, windows and doors. Apart from that, we also identified that having this massive LiDAR point cloud of the whole city was really useful to evaluate image-based reconstructions. So we decided to use a state-of-the-art method and create 2 different reconstructions of the whole city, one with each kind of imagery. And we evaluate this in different areas of the city. We decided to use the tiles in which the LiDAR point cloud was divided. And to do this evaluation, we used different measurements, for example, the number of points, the mean accuracy, in which we found that areas with river has the worst results. And then we also use precision, recall, and F-score. F-score gives us a measurement that not only takes into account the accuracy of the reconstruction, but also the completeness. And we also found out that these areas with rivers and also with parks gives us lower results. So it was worse, the F-score in that areas. And yes, just to sum up, we present an annotated labeled point cloud of the city of Dublin that is really dense and has a very diverse classes. And this dataset is publicly available, and we showcase 2 different applications. But this can be extended to other tasks, for example, to do semantic segmentation. And just mention that we presented this work recently, last week in the MVC conference. And I will be in the poster, so if you have some questions about it, we can discuss it later. Thanks so much.
Well, thank you very much for your attention so far. That was basically the end of it, of this part, and now we go over into the interactive part. But in general, maybe you observe a certain general pattern of how we do a lot of this research. So first, you identify a problem that you want to solve, and it's always good to identify a new problem, to be a pioneer in a certain area. So that's maybe the case in many of these works that you saw. Then you have to model it in an appropriate way, so to come up with an idea how you want to drive its solution. And then having the data is a crucial problem. And in many of these works, you see we had to create our own data or to curate them, which is a tedious and cumbersome work, but it also pays out, because if you are the first one to present a data set, you also get recognized in the scientific community. Well, then you have to devise a certain model to solve the thing, and here is where the secret sauce of tuning the network parameters gets in, and that's where we have a lot of parameters and a lot of experience in the team meanwhile. And then in the end, you still need to come up with some metrics, which are sometimes maybe not out there, to evaluate your work and maybe also to justify that you did some contribution to the field. So that's kind of how typically such deep learning work is going. And with that, thank you very much, and please come around and talk to us at the posters. Thank you.